Hey, math people. This is lecture 2 of our run through Calculus 3, the first chapter of it at least. So we introduced this concept of space in the last lecture, the 3D coordinate system. And we are now going to need a different tool, another tool to describe calculus in this new realm. We need the vector. So what I'm going to do is I'm going to start by defining it, going over some of its properties, view it in R2 and R3, go over two important concepts with the vector: magnitude, unit vector, its properties, and then just see it in practice. Remember, this video is for you, Anthony. So the point is, pause when you need to, use the timestamps. Let's do some math. All right, so a vector. It's a mathematical object, and you may know the phrase that has a what again, if you know it? Has a magnitude and direction. So it's an arrow. Starts at a point, ends at a point. Nothing too crazy. And what we do with that arrow is we can call this some vector AB. And I'm going to show you some notation for it. Or we can call it vector V. Here's the notation right now. You can either put a capital A and a capital B here to denote the initial point of the vector, which is like the tail, and then the terminal point where the vector ends. So point B here, which is like the tip. So you could write capital A, capital B here. But sometimes we just call it, like, you don't call me head, foot, guy. I hope you don't. I have a name. It's Math Man Grill, we'll say. And it's same thing here. We can name this vector. We can call it V. So what we do to name a vector is we put like a little arrow up top to denote, hey, this is a vector. Sometimes you can just skip drawing the bottom piece. It's called a harpoon arrow. Some people do this. Some people just bold it. It's a little bit easier when you have access to a keyboard and you can type it out, but it's bolded. You can also write it in terms of its components. So that's a word we use here. So like, maybe this vector from A to B goes 1 up and 3 right. So we would go 3, 1. You're changing the x component. So 3 right is x is left, right, and then you're changing the y component up, down. So 3, 1 it could be. And we use these special vector brackets. These are not greater than or equal to symbols. They're kind of like a little bit wider. That's one way of speaking of it. Another way of speaking of it is to write whatever that x component change was next to an I, and then whatever that b component change was next to a j. We call this standard basis vector notation, where we just strictly define I to just be one change in the left-right, J to be one change in the forward-backward, and then K would be the one change in the up-down. So it's just another way of writing it. So these are special vectors. You could write them as their bolded counterparts. So big picture is that a vector has a magnitude and direction. Okay. We can do this thing called vector addition. So we can add vectors, When I give directions, I don't just say, directions to the city. I don't just give, okay, you want to go north 13 miles and then east 14.7. No, you got to give like all the streets. You go in different directions and you change directions all the time. So yeah, you can add those together, right? So you can go vector u plus vector v to end up at this new point, or you can go vector v, vector u to end up at this new point. The fact that you can interchange those, this is called the parallelogram law, because if you were to draw vector v and u, just kind of based on the differing order that you apply it, either v plus u or u plus v, that outer rim of what that would look like would be a parallelogram. So if you went u first, then v first, or when you went v first, then u first. Together, both of those pursuits create a parallelogram. All right. We also have vector scalar multiplication that comes with vectors. So a vector has a magnitude and direction. A scalar does not have a direction. It has only a magnitude. Only a magnitude, only a number. So like the number 2 is just a scalar. The number 0, the number million. These are just scalar values. But when you throw that little hat on top, it becomes a vector, and then it has a direction now as well. And it's more than one component. All right, a scalar is just one component. Anyway, c is a scalar, just a number. So what that is it's like stretching a rubber band. So if you have a vector pointing in some direction, maybe it's, what would this be? This would be 1, 2, where it would be 1 to the right and 2 up. This is the vector 1, 2. What I would do is, let's just say I wanted to go a little bit further. I wanted to do that again, 1, 2, and then 1, 2. So I want to do that twice. I can just multiply that vector by 2. I can just tug on the rubber band, and I get a longer vector. I can also shrink it. I can also kind of make it a little bit smaller of a distance. Maybe I only want to go half that amount. And I can always go in reverse as well. So just like how a slope could be positive, a slope vector can also move in like a negative direction. You can have negative components for a vector. And you can stretch that out as well, if you'd like. All right, vector subtraction. Yeah, so you can also... So there's two different ways you can kind of view this. You can think about it as like some vector u and some vector v, and then vector v is like the negative version of, so like you have like a -1 scalar in front, and you can kind of think of it as this distance if you're going to do u minus v. You can also view it this way. But you can also do subtraction. You can vector, you can add vectors, you can subtract vectors, and then you can multiply them by scalars. That's all we know right now. There's other operations, but those come in the next 2 lectures. So in R2, it would just look it would look as you'd expect in both of these. But in R2, it would just be, maybe connecting from the origin to some point, like 3, 2. So, you just write this in vector bracket notation, 3, 2. This would be maybe some vector A, where its components are A1 and A2. Those are subscripts. And then if you had some vector A in R3, you just add another component. So you're also moving in some Z direction as well. That's all there is to it. All right, so vectors are arrows. Enough said. Find the vector representation if we're connecting this ordered triplet, and I'll just go ahead and graph it. What if we wanted to graph the vector connecting 1, -1, 2 to the point 3, 5, -8? There we go. So a vector connecting blue to green. What would that look like? What operation might you have to do to figure out that distance, that change, the difference maybe, in the x component, the y component, and the z component? Give it a go. 3, 2, 1. So hinting at it, hopefully you're thinking, okay, difference between these x components. Okay, how can I find the difference between 3 and 1? How do I get from 3 to 1? I add 2. So 3 minus 1 is just that 2, and you just do that for all 3 components. So the vector that would connect, so this would be the arrow that connects blue to green, would be the arrow starting at blue that goes 2, 6, 10. So this would be like 2 times the vector 1, 0, 0, 6 times the vector 0, 1, 0, and then -10 times the vector 0, 0, 1. So you can either write it in vector bracket notation or standard basis vector notation. These mean the same thing. Okay, so I wrote the little arrows right here, but sometimes they got special hats. I usually use special hat notation, but I was just, sometimes I use special hat notation for I, J, and K. Sometimes I just use the arrows, but generally special hat notation is used. All right, so how can we find the length of this vector? So I have a vector that connects blue to green here, right? Well, how can I figure out how long it is? Oops. Right? Maybe I want to figure out the distance that I need to travel between these two. Actually, wait a minute. Distance I need to travel. Isn't there a formula for distance that I need to travel? Can't I apply it? But here's the thing. Within that formula, right? Within that formula, we had to apply the difference, the change in the x's, change in the y's, and change in the z's. Haven't I already done that? So what do I have to do with 2, 6, and 10, -10, to get the distance? To get the distance between these 2 points. Here's the answer: 3, 2, 1. Yeah, actually I showed it. Right. Remember, it's the distance is the square root, and then it's of the sum of squares. Where what you're finding there is the difference between the x's, difference between the y's, difference between the z's. You already did that. So yeah, we're just finding of the vector, we're just taking the components, we're squaring them, we're taking the sum of the square and then the square root. So we end up getting square root of 140 here. So this number represents the distance. So let's just say x, y, and z represented feet. it would be, square root of 140 feet in between blue and green here. All right. Now, what if I wanted to find how long a vector is, which is literally what I just did right now with the points. We define this. You can see here, I wrote this kind of weird new notation. I wrote these bars and then V and then, you're like, what is going on here? Okay, well, this is known as the magnitude of the vector. So a vector, again, has a direction and a magnitude. So how do you pluck out just the magnitude? So that's what we're gonna do, is we're gonna, how do I, if I have a vector, which has a magnitude and a direction, how do I just pluck out the magnitude? And then what's going to come next is how do I just pluck out the direction? So this is the process of just taking the distance between the 2 points, or the magnitude of the vector. They're the same number, the same value. And we use kind of like an absolute value, because here's the thing, right? If we think about the absolute value of the number -2, right? It's just the number 2. Well, I know the absolute value equation is the square root of that number. So in this case, -2 squared. These are the same thing. So if I have multiple components, I'm just taking the sum of all those components, whatever the next pieces may be. And I can do this, is there a fancy word for this? Infinitum? Oh, is that right? I hope it is. I can just do this forever for any n-dimensional space. I can just add the, additional components. So in a 4-dimensional space, whatever that 4-dimensional distance may be, or the magnitude rather of a 4-dimensional vector, which does carry weight. That is important. Whether or not it has contextual application in the spatial sense is a different conversation, though, because it depends on what the variables are defined as. Blah, 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 right? All right, so yeah, in 2D, it just looks like this: square root of sum of squares, all underneath the square root. Same thing in 3D. It's interchangeable. The reason why I kind of brought up this square root of something squared being kind of like absolute values idea is that sometimes we use the 2 bars to tell the reader very clearly this is of a vector. Sometimes we get lazy about it. We're just like, you get the idea, which is kind of weird that we do it that way. Okay, so this is how we pluck out just the magnitude. So remember, vector has a direction and magnitude. How do I pluck out just the direction? All right, so the way we do that is we just divide out the magnitude, right? Because we have a direction that's embedded implicitly inside of the vector. 2, 6, -10, that vector connecting blue to green here it's got some length. The length being square root of 140, right? That's what we got from this expression right here. So if I divide out, I scalar multiply really by 1 over the magnitude, what I'm getting then is a vector of magnitude 1, right? Because if I know the magnitude of this vector is root 140, right? And I divide it by root 140, then I'm just getting a magnitude of 1. So you can't really get rid of the magnitude to a vector, but what you can do is you can divide out its magnitude, and that creates what is called the unit vector. So you would just take that vector, divide out its magnitude, and then at least in some ways what this vector, it's still a vector, represents is just the direction. So from this point, this blue point where we started, it would point in the direction of green, right? But it would just be of a length 1. So it would just be very small. So it'd just be like me being like, hey, it's in that direction, That's how we kind of pluck that out. All right, anything else here? So vectors have some properties. Here they are. I mean, yeah, some of these are implicit, so this is parallelogram law right here. You can kind of change the order in which you add up the vectors. There is such thing as the 0 vector. So if you add 0, 0, if I say, hey, go 0 units right, 0 units up, 0 units forward, you don't really go anywhere. If I tell you to go 1 unit to the right, 2 units up, and I told you to do the exact opposite, go 1 unit left, 2 units down, you're gonna be back where you started. You can distribute the scalar multiple. You can also distribute a vector to 2 scalars. That one's kind of interesting. I don't know why you would do this one. You can also just add up the scalars first and then multiply it in. You can kind of pluck out a scalar or just distribute scalars one at a time. And then just implicitly, the scalar that's like always in front of any vector is 1. Yeah, so we use these little, you can read through the comic if you want to on your own. We use these little hats, these little special hats to denote the standard basis vector notation. Sometimes I might be a little lax about that. That's kind of the bad thing about, or like the unfortunate part about like Calc 3 in particular, is that we tend to get, in my opinion, we tend to get a little loose with our notation a bit. We kind of go back and forth where we go like, yeah, double bars for magnitude, but single bars are good too. You know, yeah, we can give I, J, K this the special hat if we want to, but we don't have to. You know, like vectors, yeah, sometimes we bold, sometimes we put narrow, sometimes we use the bracket, sometimes we use I, J, K. It's whatever we're feeling, and that's, you know, it's a double-edged sword because we want to have conformity in how we communicate rigorous language like mathematics, but at the same time, you know, it's just notation. So like, it just scribbles on a page, right? But we're talking about the same thing. That's what's important. All right, last little round here. Go ahead and try to just do vectory things. We know vector addition. We know scalar multiplication. We know how to find magnitude. We know how to find the unit vector. So I'm giving you 2 different vectors here, A and B. Just do some math with it. Give it a go. Give this one a real go. This is the one you actually want to practice, okay? 3, 2, 1. All right, vector addition, you're literally just taking the sum of the x components, y components, and z components respectively, right? First, for the next problem, I would distribute the 4 into all 3 components, and then the -2 into all 3, and then just add the 2 vectors thereafter. Finding the magnitude of A, which is the distance in between, you know, the tip to tail, right, of the vector. It's just square root of sum of squares. I'm going to say that all the time in this course. Square root of sum of squares. So be ready. All right, this next one was just first taking the difference between these 2 vectors, and then, so I did that right here, and then finding the magnitude of that distance, so square root of 134. And if I wanted to find the unit vector of AB, so what would that be? That would be if I were to start at some point, and then I were to give you some directions, you know, 1 up, 2 to the left, 1 to the right, 2 backward, 4 up, and then the same thing for B. And then if I'm just like pointing, I'm just like on the street, I'm like explaining to you the different directions that you need to take on the street in order to get to where you need to go, I would just be like pointing to like that end destination. That's what this would convey, the pointing. So what I did was I found A plus B. I did, right? Yes. Oh, I already did over here. So here it is, -8, 1, 5. And then I just took the magnitude of that. So that's the square root of sum of squares. Yeah, there it is. So this is the equivalent of me just pointing after giving you a lot of directions. Did I give you a lot of directions right there? Hopefully I gave you some magnitude too, because that makes the vector. All right, that's it. Math on.